pleasure to be here for the 20th anniversary and the 10th. My first IGST talk was 10 years ago. So let me thank the organizers for inviting me, and it looks a very exciting week coming. And this is a little bit of a topic that I think this is, if I have a legacy, at least for the IGST crowd, this is going to be what I am working on sort of my whole life, of course with other things. And yes. And of course, this work, there is no way I would be able to do alone. There are some amazing collaborators, especially Denise has a poster. So this will be another spot to discuss about these topics that I will talk about today. My main concern will be to present this paper from last week. And there is another paper, parts of each of which you have heard before in previous IGSTs, but I want to try to show you like the way we understand things now. And without wasting any time, let's go to, okay, IGST. What is the biggest thing that came out of it? N equal to 4 super young means is integrable, and we are still working on being able to use integrability to calculate more and more observables. But if you stick to 4 dimensions, there is a big open question. I mean, when we write our grant proposals, we say that we want to go to QCD, so we really need to try, yeah? So what do you have to do if you want to try? So the first simplest step after n equal to 4 is to study n equal to 2 super CFTs. And the best way to do it, in my view, is to begin by orbifolding n equal to 4 super young meals, because what you get is integrable theories, and then perform marginal deformation. And by doing that, in fact, what is happening is that you are capturing a very big subset of the landscape of n equal to 2 theories. And this construction is also fantastic because it generalizes to n equal to 1 theories. So with this in mind, this is my favorite toy model, which you have all seen many, many times. So we begin by doing a Z2 orbifold in n equal to 4 super young males. And then we marginally deform along the conformal manifold, which in this case, it's 2-dimensional. When the coupling constants are equal, we call it the orbifold point, which is the theory that we know is integrable. And as we go away, all the way to the point where one of the 2 couplings are 0, we obtain super QCD, n equal to 2 super QCD, which you could say is the most physical n equal to 2 super conformal theory. And the most important thing I want you to know for this theory is that happily in n equal to 4, all the fields were in the adjoint representation of the color group. Now we have 2 color groups, 2 SUNs, and I try to put color so that I attract your eyes. So there is one type of objects that are adjoined under the one, another adjoined under the other, and we have bifundamental fields. And I want to say that all the new physics really comes from precisely that. So let's go for it. So for this talk, I will first have a shut up and calculate approach. And this is really just explore how much can we do with coordinate Bethe-ansatz. Up to very recently, we didn't even know how to write 3 and 4 Magnon eigenvectors. Now I will be able to write them down. And for that, we will see that long-range interactions appear. And then I will have a more beauty way, top-down, where I will search for new symmetries, and I will try to convince you that we need to go away from the Lie groups that we love. We need to go to groupoids or category theory if you like more math. This is the future. So let's begin with a shut up and calculate approach. So, and I really tried my colors, so let's start. First of all, n equal to 4, let's say it has the 2 x and z fields, and they are rotated by a subset of their symmetry, which is an SU2 rotation. But the moment you do the orbifold, this is broken. So naively, we do not have it. Now, when you try to construct vacua, if you do a ZZZ type of thing in n equal to 4, now you get 2 of them, and I try to label them with the 2 colors, blue and pink. So this is a very important thing for this talk. And there is another type of vacua, which is bifundamental vacua. And these we're studying in this paper, and I will not repeat anything other than showing you this equation and make you want to ask questions at the end of the talk or by the poster. So this talk will be all about this. So here we are, one magnor around the ZZZ vacuum. So this bifundamental excitation, precisely because it's bifundamental, it interpolates between the two different vacua. And there is no other way. There is no way out of that. And because we have the Z2 of the orbifold, there are, in fact, two 1 magnon eigenstates, and they are Z2 conjugate to each other. And this is their energy, 1 magnon, and you see this is very different from this. Yes? So there is some very rich physics in this model. And also, if you do Z2 together with parity, is precisely equivalent to reading the chain backwards. Now, two magnons. Two magnons were also, this is my childhood, that's why I said now I feel old a little bit giving this talk. So there are again there are two eigenvectors, and in this time we interpolate between one type of vacuum, we change to the other, and then we go back to the other one, and they are again Z2 conjugate to each other. And when we look at the amplitudes, the scattering coefficients, they come with a pattern, and the pattern is precisely, so this is you can say the XXZ scattering matrix with anisotropy parameter kappa, but now both of them appear, one with kappa and one with 1 over kappa, where kappa appeared here is the ratio between the two coupling constants. Yes, it's the way you go from red to blue. And yes, you should really think that these things are colored. Now, what is going on and why it has taken so long to make progress? If all you know in life is coordinate Bethe ansatz, and you try to find a solution for 3 or more magnons, you will simply fail. And you will not only fail if you just try coordinate Bethe ansatz, even if you add contact terms, a finite of them, you will still fail. There is no way to do that. So what we had to do, and the reason why you fail is precisely because the naive Young-Baxter equation is not satisfied. And this is why the colors are super nice, because now you can follow this guy is this guy, this guy is this guy, and so on. And you see how you should put your S matrices, and they fail. So what did we have to do in order to succeed in finding eigenvectors? By the way, this is a physics problem. It has nothing to do even with integrability. You should be able to find eigenvectors, yes? So what we had to do is we had to allow, at least for the infinite chain, for an infinite number of position-dependent corrections to the coordinate Bethe ansatz. It's almost like saying we don't know anything, we admit we are stupid, we will try the most general thing we could ever do. So this is the original ansatz now for 3 and for 4 magnons. We add these guys. And n and m and also r here are integers, which precisely label the distance between the magnons. So the way now you understand is you set up your problem and you try to solve the eigensystem. And what you find is that these d's, the corrections to the coordinate Bethe ansatz, they arrange themselves in a lattice, which is here. I first will explain the 3 magnon, and then you can imagine in your head the 4 magnon. So these are the distances between the left, and these are the distances between the right. And the eigenvalue equations, they arrange in 3 classes of equations, where the 3 magnons are far away all from each other, when 2 magnons are near and 1 is far away, and when all the magnons are all next to each other. And the colors that I have here, they tell you what they are solving for. Yeah, and again, for 4 magnons, you should imagine the same thing, but in a form of a cube. And what is important is that for any d, these equations, if let's say you want to solve this guy, they relate them with their nearest neighbor. So you are solving like a little cross. And of course, all the crosses are related to each other. So you do this, and you start solving, and you discover that if you only impose these eigenvalue equations, you can in fact not fix all the coefficients. And this is okay, we are not crazy. This makes sense because we have not yet imposed any boundary condition in this infinite chain. What we will do, because at this stage we don't want to impose boundary conditions actually, is we will do a trick. we will remember that there is this very important Z2 symmetry of the quiver, and we will try to have further conditions on the ansatz such that this Z2 symmetry is always manifest, first of all at the level of the infinite chain, but also, and this is a little bit a posteriori, I have to say, when you take it and you close it and you impose periodic boundary conditions, twisted or untwisted, we want whatever we get to match with what we get with direct diagonalization, yes? And we discovered that this is a good thing to impose. And I challenge you to find something better. Now, here we are. We have this guess, if you wish, something the divine intervention, and then we plug it in our equations. First, the 3 magnon, and we start fixing, we start getting answers, so we get these 3 guys. Then we plug it in the 2 magnon interacting equations, and we start getting the blue guys, and we continue to this area, and we get the green guys. And what is happening, you see what is happening. You always have these factorized scattering coefficients. You always have this kappa minus 1 over kappa, which is fantastic because when kappa is equal to 1, the 2 couplings are equal. This goes to 0, there are no corrections, and you go back to what you know and love for normal coordinate Bethe ansatz. And then as you start going to bigger and bigger distances, you get this parenthesis in front of this factorized beautiful part, which they have the energy of the 3 magnons, the total energy and the total momentum, and sometimes also other momenta start coming in this parenthesis. I will not bore you with writing huge, horrible expressions. So the point of this exercise is for this special solution that we started with this assumption, if you wish, you can completely solve for all these coefficients, and they have this very beautiful factorized form, and they can also be captured in a generating functional. And I want to say that the power of which we are not even close to comprehend. But you can ask me. Fantastic. So we have the solution now, and we want to ask for its properties. And first of all, already the scattering coefficients, they factorized, so they just obey the Young-Baxter equation. Now, what is remarkable is not this. What is remarkable is that also all these crazy corrections, infinite numbers of them, in fact, they also obey some type of Young-Baxter-like equations for all the integers. And here I write for you what they obey for the 3 magnon problem. This Y is an object that you could define as the Young operator. It's the thing that appeared in the very first paper that Young wrote. And I write it here. I don't really want you to look closely because you will maybe, it's too much. And it's also unitary. But we have this infinite tower of equations. This is not magic. There is a reason, right? Now, not only that, there is something even more amazing, which is in the paper that came out last week, which is the following. Now we have a way to relate an n+1 magnon eigenvector to an m magnon eigenvector. How do we do that? We do something that I like to call smearing a magnon. So basically, you allow to sum all the possible, you pick your favorite magnon, let's say the one on the right, and you sum over all the positions it can take. And also you have to localize it by setting its momentum to 0. The moment you do that is a simple exercise to see that the 4 magnon eigenvector gives you the 3 magnon eigenvector. And this is, by the way, this we also started testing with XXX, XXZ. This only gives you factorization. But of course, here it gives you way more things. It gives you relation between the 4 magnon Ds and the 3 magnon Ds. And the best way to see the consequences of this crazy equation is to think at the level of the generating function, which captures all the Ds. So first of all, by taking limits, you can see that, for example, if you are smearing all the right one, the right magnon, this is equivalent to taking Z to 1, and you relate directly the 4 with the 3 magnon generating function up to a very concrete pole. If you do this for the middle guy, you get a finite answer. And clearly also if you do this for the x, you get the same, but the pole has here 1 minus P1 x. So then this becomes like OPE game into DCFT, and we love these games. And you can do it, and you can patch the poles together, and you get an answer. Clearly here I'm not presenting all the details of the answer, and it's a 3-line thing in the paper with also references to the appendix. But you see what happens. This 4-magnon function, it organizes according to the poles. These are 3-magnon stuff, 3-magnon stuff, 3-magnon stuff. It's an amazing equation. Now, why this is happening? This is really crazy. The reason why this is happening, as I will try to convey, is that there are more symmetries than we thought are there. Of course, we are only at the beginning of really understanding what they mean, but let me try to tell you what they are. So the most important thing, if you want to think about in terms of symmetries, the most important thing I want that it stays with you is that n equal to 4 super Young-Mills was a very lucky thing. All the fields are in the adjoint representation. So the only thing you could put on a lattice side was an element of the singleton representation of n equal to 4. And the total space of spin chains is this beautiful product. And I have to insist that all the chains that we know how to solve, they are only of this form. We don't know how to do other things professionally. So what I am trying to tell you now is that if you want to go beyond n equal to 4, and here I'm talking about n equal to 2, but n equal to 1 is the same, you are not having unique singleton representations anymore. You have at least 2 distinct ultra-short representations of the superconformal algebra. So this beauty is out of the window. That's the most important thing to remember. This is out of the window. And let me elaborate on this. So precisely because we want to be in the planar limit and we want to color contract matrices, the one after the other, some orderings are allowed. For example, here, 1, 2 can go after, but some other things are not allowed. If you end with the 2, you cannot start with the 1. This will give a off-planar contraction. So in this paper already, we had found at least a physicist way to talk about this by saying that these spin chains are dynamical. And what we meant by that is that you can always think of n equal to 4 states as the mother theory, and then go and choose your very first index. Here is 1, here is 2, and then just color contractions will give you the rest, and there is nothing for you to decide. Now, in this paper, we have, I think, the most elegant way to describe this phenomenon, and that's actually the only way also to talk with mathematicians. And this is that the Hilbert space of these spin chains, it forms a path groupoid. And what is a path groupoid? It's something super simple. Here is the picture of the quiver. Follow the arrows. As long as you are following the arrows, the operators you are making are correct. And this language is basically precisely the language that is used by Felden and Wren in this beautiful paper. And it is a one category. I'm not going to tell you any crazy math here. I just want you to remember, follow the arrows. That's what it is. Now, that's not all. There is even more symmetry in the game. And that now the R-symmetric algebroid, we call it. If you don't like, I'm not attached to any name. This is what acts on these spin chains. So in n equal to 4 super Young-Mills, very happily, we had an SU2, and the X and the Z, they were forming a doublet of this SU2. Fantastic. Now, as I already said, we lost this SU2, and the reason is clear. You cannot put in a doublet oranges and apples together. It's not allowed. And here is an orange, and here is an apple. This is adjoint, and this is bifundamental. The only way to circumvent this problem is to drop the Lie algebraic setting and go to a Lie algebroid. Let's do this. And let's do it as stupidly as possible so that no one cannot follow, basically. So in n equal to 4, we have a SU2 algebra, and we have raising and lowering operators, and they tell us how to go from X to Z. Now we have lost the SU2, but let me nonetheless define raising and lowering operators. Now I give them an extra index, an index 1 and 2, which has to do with the Z2, or the fact that I have two color groups, and I simply prescribe how they act. Clearly, these babies, they know about the color because this was an adjoint object and this was a bifundamental object. So this person is responsible for changing the color representation of this guy to this. Yes, so this is not just Lie algebra. Now, how should you understand this algebroid? Basically, you should just understand this picture, but let's walk through it together. This picture is only for single letter words. In a second, I will tell you how to string single letters to bigger words. And this picture, so these are the vector spaces on which we act. And these are the generators that tells us from where they start and from where they end. And in this picture, I have an extra element defined, which you can understand precisely from here what it is the mirror, is the Z2 symmetry of our quiver. It changes 1 to 2. And more explicitly at the level of fields, it makes Z11 to Z22 and so on. Yes? Fantastic. But you know, if I was just staying there, that would be silly. Things really become non-trivial the moment you start having at least two sites. So for n equal to 4 super Young Mills, we were very lucky, and we could use the trivial coproduct like this to act on two sites. And here I'm acting with the raising operator. Now, we have lost now this thing, but let's, for the beginning, be stupid and try the naive coproduct. The moment we do this, we get wrong, not allowed, because after 1, you cannot have a 2. How do we fix this? Our algebroid has an extra element in it, which is this gamma, this Z2 odd operator. So we change our coproduct to a non-trivial one by having here an explicit gamma. By the way, this is a little bit conventional. You could choose to put it here, but this is a convention that for us the first index is always important. Yes? And the moment we do this, the contraction is allowed, and this is a very good guy. And not only that, I can generalize this construction for any length simply by putting gamma, 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 gamma as many times as you need. And of course, the sigmas here are always the sigmas with the indices 1 or 2, that they simply obey a simple SU2 algebra. Now, fantastic. So we have some construction going on. Now let's take this and let's try to see what this does to the Lagrangian. First of all, before even doing that, we have to remember that the Lagrangian is a single trace operator. So to do my calculation nicely and also being able to show it to you, I will cut open the trace. And to do that, I need a prescription, and this is my prescription. I'm not the first human being to think about that. And with this prescription, I will show you an explicit calculation that this SU2XZ is a symmetry of the Lagrangian. This is the guy that was supposed to be broken and lost. And in fact, the whole SU4 is there, but I will not show this to you because I only have 30 minutes. And the fastest way to do the calculation is to use superfields, although in the paper we also have done everything in component. We went through all the pain, and there are many pages really doing this. So let's just do the superpotential. Here is the superpotential at the orbifold point where the two couplings are equal. We cut it open. This is the cut it open superpotential. And we simply apply the coproduct the way I showed you. Things just beautifully cancel. I put my colors to show you how things cancel, and you get 0. This is the symmetry of the superpotential. And Kähler also trivial is, the Kähler part is also trivial because it's a singlet. That's not enough. We want to go away from this orbifold point and capture the whole conformal manifold. How do we do this? The way we should think is that this coproduct that we wrote down, it somehow has to get deformed by the marginal deformation, which is this ratio of couplings. So this, as you will see in a second, it's captured by a Drinfeld-like twist object, which you simply read off from the F terms. And if you want to do the full SU4, you also have to include the D terms. This is something we understood when we were at MBI. And if you also want a physics understanding of this, it all comes from Seiberg and Witten. When there is a B field transverse to our D3 branes, open strings ending on these D3 branes, see a non-commutative geometry. This is what is happening. Here is the twist. It's just precisely that. It puts G1 and G2 here in the equation and also deforms the coproduct the usual way. So we compute in this way and we get this answer. So all that happened with respect to the previous equation is that I dressed my guys. By the way, again, this is only for the SU2XZ. If you want to go to the full SU4, pain starts. So you simply dress by kappa to a power, and this power is an operator that asks the field what is your first open color index, and you get 1 if it's 1, and you get -1 if it's 2. And this object also commutes with gamma in this way. So we have a construction, and we do the same thing. The only difference now is that there is G1 and G2 in the superpotential act. Everything is in the way that it's made to work. Super quickly, we didn't only stay into this. We also tried to use this symmetry to construct multiplets spectrum. And these multiplets are, I mean, it is very surprising that they exist. So for example, when we study n equal to 2 theories, we have Coulomb's and Higgs branch operators, and actually also mixed branch operators. And for n equal to 2 superconformal algebra, they have nothing to do with each other. Well, now with this coproduct, you can start from a Higgs branch operator, act, and make an SU2 multiplet relating all of these guys. And not it's just that you are having fun. These things, they come with kappas. So G1, G2 is everywhere sprinkled. And if you brute force diagonalize your Hamiltonian, you can check that you get these kappas in precisely the right place. So this is pretty amazing. And we also were able to do for 2 sites, for the full SU4, here is the 20 prime, and here is the 15. There is no detail here, but clearly the kappas are where they need to be. Fantastic. So let me summarize what we have. First of all, I gave you a generalization to the coordinate Bethe ansatz that has long-range interactions, infinite of them for the infinite chains. And doing this, I was able to obtain 3 and 4 Magnon eigenvectors, which were not there before. These eigenvectors, the coefficients in front, they go all together, conspire to form an infinite tower of Young-Baxter-like equations for every integer that signifies the distance between the 2 magnons. Not only that, the 4 Magnon eigenvector that we calculated explicitly and the 3 Magnon eigenvector that we calculated explicitly are related to each other in like a very interesting way. Yeah. This is something that I only said in one sentence, but it's important. By imposing periodic boundary conditions to the 4 Magnon solution, we can check that we get the same thing as direct diagonalization, so no bullshit. And there is a novel groupoid structure. In fact, there are 2 one-category structures which form a bicategory together, if you like math words. And we check the Lagrangian and a little bit of spectrum. And there is a plethora of things to do. This is a completely, like this is just a few things that came into my mind that I should say, but please ask me and I will tell you more.
So we have time for a few questions. Nicholas?
Thanks for the talk. do you consider your model integrable in the first place? I mean, I think there is a fundamental difference between an integrable model and a non-integrable model. And even if the model is non-integrable, there might be methods to address it, right? Even, I mean, especially if it's nearby to an integrable model, but is it integrable?
So at this moment of life, I will remain agnostic because I want to be super careful. Although I want to say something, which is, I think, very important. I think this type of stuff, a normal integrable person would not be able to understand. And that's why I really stressed the category structure. Like a normal person that is raised with XXX and XXZ and even XYZ cannot understand this paper. And there are matrices and Young-Baxter equations and everything. So basically what I'm saying, there is definitely more structure. I cannot at this stage tell you if it's integrable or not, but the only way to answer this question, you have to go to this game. There is no way out. Otherwise, you are simply asking the wrong question.
And then maybe just a very short one. Do you close your traces with different colors? Can you do that in a gauge?
No, so if the outside has different colors, you are not allowed to close them unless you put a defect. I am only closing when the same color is outside. That's why I closed only 4 magnons and not 3 magnons.
Edina? Oh, she's up there.
Yeah, thank you for the nice talk. I wanted to know if this structure of the smeared magnon is also present at the orbifold point.
It is trivial for the orbifold point because these G's that I had, they are actually equal to 0. So there is nothing to learn. Yeah, it's here. This is directly equal to 0. You have to go away to see this thing.
Okay, thank you.
Are there any more? If not, can I, since you have the slide up, can you say a little bit more about what the H's and the C's are?
So the H is the Z2 conjugate of G.
Okay.
So, you know, you solve and there is blue and red and there is red and blue. Okay. And this is something that has G's and H's in it. It just looks ugly and I packed it all
That's
in an
the one that's 3 lines or something?
Yes, that's pretty ugly.
If there are no more questions, let's thank Elli again for a nice talk. So I guess we have our coffee break now and we'll reconvene at 11:25.